Hello everyone and welcome back to Measy Science channel. This is Sofwan Al-Fallata. In today's video, I'm going to talk about second order homogeneous differential equations, and I'm going to apply the auxiliary equation or the characteristics equation in order to solve for the complementary function of these differential equations. So don't forget to like, subscribe and share with your friends so that you don't miss out our future videos. So let's get started. So in order to understand the content of this video, one has to have a basic knowledge of calculus, that is differentiation and integration, as well as how to solve a quadratic equation. So the equation here is an example of a second order linear homogeneous differential equation with constant coefficients, that is y here is differentiated twice, whereby y prime prime is the same thing as d squared y divided by dx squared, and it is a linear differential equation because the power of this second derivative of y is equals to 1, which is known as the degree of the differential equation, and the differential equation is equated to 0, and that's why it is a homogeneous differential equation. So in order to find the solution of this differential equation, one has to apply the auxiliary equation, which is in form of a quadratic equation, and it is also known as the characteristics equation. So the solution to this second order linear homogeneous differential equation consists of only the complementary function because the equation is equated to 0. So the solution of the complementary function depends on the roots of the quadratic equation obtained, and there are three different cases. The first case is when the roots are real and distinct, that is, the roots are not equal. Then the solution of the differential equation will be of this form, where c1 and c2 are constants and k1 and k2 are the distinct roots of the quadratic equation. And the second case is when the roots are real and equal, then the solution of the differential equation will take this form, and when the roots are complex conjugates, such that the first root k1 is equals to a plus ib, and the second one k2 is equals to a minus ib, where a represents the real part of the root and b represents the imaginary part, then the differential equation will have the solution of this type. So before taking any examples, first of all I will derive the solution for the differential equation when the roots are complex conjugates. So when the roots are complex conjugates, then k1 and k2 will take this form, and we are going to use three equations for the derivation. First of all, we are going to use the solution of the complementary function when the roots are real and distinct. As we discussed earlier, this is the solution for the differential equation, and these two equations here are trigonometric identities that says cos of bx plus I sin bx is equals to exponential ibx, and the cos bx minus I sin bx is equals to exponential minus ibx. Okay, so in order to get the solution in terms of the complex conjugates, then we have to substitute the value of k1 and k2 in this form. So that implies that y of x is equals to c1 exponential k1 is a plus ib multiplied by x plus c2 exponential a minus ib multiplied by x. And then by the virtue of indices, we can separate the exponential as the product of the two, ax exponential minus ibx. So substituting these two equations, instead of exponential ibx we write this, and instead of this we substitute this, then therefore y of x will be equals to c1 exponential ax all into cos bx plus I sin bx then plus c2 exponential ax cos bx minus I sine bx. So now collecting the like terms, c1, okay, a exponential x ax is common in this part and in this part of the equation, so as cos bx and I sine bx. So we can write this. Then what's left here is c1 for the cos, c1, and what's left here is plus c2, then plus also exponential ax and I sine bx is common. Then what's left here is c1, and what's left here is minus c2, minus c2. Okay, so if we expand this bracket we will get this. Now let c1 plus c2 to be equals to k1 and capital K1, and c1 minus c2 multiplied by I is equals to capital K2, while the roots are small k1 and small k2. So substituting this in this equation, then y of x will be equals to exponential ax cos of bx, all this is k1, plus exponential ax sine bx, then I multiplied by c1 minus c2 is k2. So factorizing exponential ax outside, we will have k1 cos bx plus k2 sine bx, which is the solution for the second order linear homogeneous equation with complex roots. K1 and K2 here are constant, just like C1 and C2 in the equation we defined. So from here we can just let K1 to be equals to C1 and K2 to be equals to C2, since constants are constant. So if we were given the condition in an example to find the constant, the value will be the same irrespective of the notation of the constants we use in the equation. So this is the first example. For real and distinct root, we have del squared y divided by the x squared minus 8y dx plus 15y equals to 0. So first of all, we are going to write the differential equation is in this form. The y plus 15 of y equals to 0, where d is known as the discriminant. Then we factorize y outside, y equals to 0, and we divide through by y so that we obtain the auxiliary equation, which is in form of a quadratic equation. So now this is a factorizable quadratic equation, and the two factors of this equation are minus 5d minus 3d plus 15 equals to 0. So then from here we can say d into d minus 5, then minus 3 all into d minus 5 equals to 0. D minus 5 is common, so d minus 5, d minus 3 is equals to 0. Then d is equals to 5, or d is equals to 3. Okay, so now for real and distinct root, we know that y of x is equals to c1 exponential k1x plus c2 exponential k2x. So k1 and k2 here are d1 and d2. So substituting, we will end up having c1 exponential 5x plus C2 exponential 3x. So D1 and D2 here are K1 and K2, and this is the solution for the second order linear homogeneous differential equation. So this is the second example, and it is for real and equal roots or repeated roots. So from here we can just directly write this as del squared minus 6d plus 9 equals to 0 if we follow the same procedure we did in the first example. And then the roots of this equation minus, we have minus 3d minus 3d plus 9 equals to 0, because minus 3 times minus 3 is plus 9, and minus 3 is minus 6. So here we will have d all into d minus 3, then minus 3 all into d minus 3 equals to 0. So d minus 3 is common, we have d minus 3 equals to 0, then d is equals to 3 twice. And then using the solution we discussed in the beginning of the video, y of x for real and repeated root is equals to c1 plus c2 times x exponential kx, where k is the root, and this implies that c1 plus c2 of x exponential 3x is the solution for the differential equation. So from this is the same thing as the second derivative of y, this is the first derivative of y. We can just choose to write it as d squared minus 2d plus 3 equals to 0, or we can write it in terms of any letter. It actually doesn't matter as far as the solution is correct. So from here, this equation is not factorizable, so we are going to use the general formula, and by that d will be equals to minus 2, which is minus 2 will be plus 2, plus or minus 2 square is 4, minus 4ac, that is 4 times 3 is 12, all over 2a, a is 1, so divided by 2. So 2 divided by 2 is 1, we will have 1 plus or minus root of 4 minus 12, that is minus of 8, all over 2, and using surds we can write this as 4 multiplied by 2 multiplied by minus 1 all over 2. So therefore d will be equals to 1 plus or minus the root of 4 is 2, root of 2 is 2, and root of minus 1. So using surds, 1 plus or minus 2 over 2 is 1, so we have 2 root 2, and root of minus 1 is the same thing as I, so d1 is equals to 1 plus I root of 2, and d2 is equals to 1 minus I root of 2. So substituting these roots in y of x exponential ax multiplied by cos of bx plus sine bx. So a here is equals to 1 and b here is equals to root of 2. So therefore the solution for the differential equation will be exponential of x only, then cos of root 2 x plus sine root 2 of x. You can also come across an equation whereby a condition will be given to you in order to determine the constants. There are constants here, k1 and k2, so k1 plus k2. So you can use that condition in order to calculate these constants value and then insert them back into the solution of the differential equation.
Okay, so that's it for today's video. I hope it was useful for you people. In the next video, I'm going to talk about particular integrals, which is a solution for the non-homogeneous second order differential equations. So if you have ideas about future videos, don't forget to drop a comment and we'll try our best to make that video for you. Thank you for watching and see you next time.